All right, welcome. So yeah, we are now in week 6, I guess, of the semester. We've talked a lot about coronal heating. Now we want to start to move over and talk more about the solar wind. And there's a connection, right? We'll talk about the fact that the magnetic field of the corona is actually stretched out by the solar wind, and we'll talk about the dynamics and the way the magnetic field is configured. Where's my outline? Yeah, so it's really just 2 questions today. One is just to think about the overall geometry, maybe the word is topology of the sun's magnetic field, because there are these closed magnetic features. You know, we talked about coronal loops a lot, and then there are these much larger features that the solar wind starts to grab a hold of and stretches out. And actually, we call them open magnetic field lines because they actually remain open all the way out to the edge of the solar system, hundreds of astronomical units. All magnetic field lines do have to close at some point, but they can be delayed from doing so for a long time. And then we'll talk about the dynamics of the solar wind, which is more the topic of the reading that we just went through. And I'll try to put some historical context there and talk about some of the possibly more confusing aspects. But yeah, the sun's magnetic field, right? You know, there's you can, if you wanted to measure the magnetic field of the sun everywhere, pretty much from the core of the sun to the surface, to the corona, to the solar system, to the galaxy, right? You can measure a value of the magnetic field everywhere. Oh, there's some audio feedback somewhere. Make sure that's all right. There's magnetic field everywhere. For convenience's sake, we normally think about the photosphere as this sort of the lower boundary condition for everything above it. Not because it's unconnected to the inside, it's very deeply connected to the motions inside the sun, but we don't have as good measurements of those. And we have ways of sort of modeling what's happening on the photosphere and also keeping track of the field to very high precision using spectropolarimetry, the Zeeman effect. Mainly what I'm going to be talking about here is taking that photospheric field and then solving sort of an extrapolation problem, right? If you know the field along the surface of the sun at the photosphere, how good can you just use that piece of information to estimate the field everywhere above it? And there are these other good measurements of the magnetic field. It's hard to measure the magnetic field in the corona, mainly because as the temperature of the corona goes up from the photosphere, the spectral lines that are typically used for this Zeeman effect get broader by 1 or 2 orders of magnitude, and all those subtle little line shifts and line splittings that happen at the photosphere get drowned out by the fact that the lines are so broad in the corona. It's tough, but there are some techniques, and DKIST is going to be giving it the best possible try to measure these things at least a half a solar radius up into the corona. And of course, there's in situ measurements. Magnetometers bolted to spacecraft can go fly through a plasma and measure the magnetic field that they're flying through. And yeah, both the coronal and in situ data are good sort of checks on how good this extrapolation is. That's usually how they're treated, just because it's a relatively straightforward thing to perform this extrapolation. And we'll talk about the methods as we go forward. Of course, what we would really like is measurements everywhere. But we have to sometimes just deal with extrapolations. One of the things that we have to keep in mind when extrapolating is, what are we extrapolating through, right? If it's an MHD plasma, what are the properties of that plasma? This plasma beta ratio that we've been talking about several times is a pretty important feature. So I've got a plot here just taken from a whole bunch of several hundred solar wind models that were produced for different parts of the solar cycle, just to look at the overall features of how does the plasma beta ratio change. And again, this x-axis is height above the solar photosphere in units of the solar radius. So the left-hand part is sort of the upper photosphere and the chromosphere. This part in the middle is the corona, where the plasma beta gets very low, right? It becomes a magnetically dominated plasma. And then if you go up into the solar wind, where are the planets here? Mercury is at 60, the Earth is at 200, Mars and Jupiter are out here at the right edge. So yeah, we're going all the way out into the solar wind, where the plasma beta becomes large. It's a gas pressure dominated plasma. And again, you remember the differences between these two. When it's a high beta, the gas pressure, the gas tells the magnetic field what to do. When the beta is small, the magnetic field tells the gas what to do, right? When you're down here in the corona, you can think of the magnetic field as sort of existing, and the plasma is sort of constrained to move along the magnetic field. The opposite, out in the solar wind, the magnetic field is just sort of a passive player, and it's the gas that determines what to do. And we'll see it's the solar wind that's expanding outward that stretches the magnetic field out. But yeah, all these extrapolation techniques have to take these changes over many orders of magnitude of distance into account to provide something realistic. Yeah, and I just wanted to give a quick summary of these different extrapolation techniques. There's actually a whole bunch of them out there, and they run the gamut. At the top of this list are sort of computationally simple tools that don't tend to take the solar wind into account very accurately. We'll talk about the potential field solution soon. But then as you go down the list, there's sort of more taking the solar wind more and more seriously as you go down. At the very bottom, we have full dynamical solutions to the 3D MHD conservation equations, simulations essentially of the entire system that are now getting pretty accurate, and they're fully self-consistent. But in between, it's a little bit of a chicken and the egg problem, as I showed here. You have to assume some things about the magnetic field, assume some things about the solar wind, and see how well they play together. We'll talk a little bit about these as we go forward. I don't think I'll provide examples of every single one here, but yeah, we'll talk about the progression here. So yeah, starting at the top, where we're not really thinking too much about the solar wind yet, we have to think about what are the dominant terms in the MHD equations, right? The momentum equation is basically F equals ma. We've got acceleration on the left, and a sum of forces acting on a little parcel of the plasma on the right. And let's just think about the corona, where the plasma beta is very low. When we start out, well, if the beta is low, then we can usually ignore the gas pressure in comparison to the magnetic pressure that's sort of hiding in the J cross B term here. So we can ignore one term. In the corona close to the sun, the solar wind hasn't really gotten going yet. So we can actually consider the flow the actual flows, the actual accelerating flows to be sort of unimportant. If the flows are much slower than things like the sound speed and the Alfvén speed, then these left-hand side terms aren't that important either. Well, we can keep going and chopping out some more terms, because the gravity term actually turns out to be relatively unimportant for the corona. If you were to try to evaluate the overall strength of gravity and say, divide that by the strength of this J cross B force, you would sort of get a ratio of velocities. I think it's the square of velocities. The escape speed from the sun, which is a gravity thing, and the Alfvén speed, which is a magnetic field thing. And, the escape speed from the surface of the sun is 600 kilometers per second. The Alfvén speed is a few thousand. So in general, gravity is usually not thought to be that important in terms of determining what the coronal magnetic field is doing. So what's left is really just one term. If you ever heard the term force-free plasma or a force-free MHD system, this is what we're talking about here, where all the other terms are so unimportant. The magnetic force, the Maxwell force, this is sometimes called, is the dominant thing. But if there's nothing else to balance against, then its actual value has to be zero. And it's interesting to try to study the properties of a system where J cross B is zero. If that's true, there's several ways to make that happen, right? You can have a zero current, you can have J equals zero, or you can have J parallel to B, right? Then their cross product would be equal to zero. And both of these things happen on the sun, right? Last time we talked about flares and flux ropes and sort of these core twisted regions that eventually become the central parts of CMEs. Those are the parts where J is parallel to B. But most of the rest of the volume of the corona tends to want to relax towards this J equals zero type solution. So we can try to figure out what that implies. In ideal MHD, the current density is proportional to the curl of B. But of course, we also know that the divergence of B always has to be equal to zero. So we have both the div and the curl of B have to be zero in this zero current situation. And we can start to think what that really implies from sort of vector analysis, right? If we know that the curl of B, if the curl of B has to be zero, we know that the curl of the gradient of a scalar is always equal to zero no matter what. So this means that we can express the magnetic field as the gradient of a scalar function. If that's true, then the div B equals zero condition actually gives us an equation that we can solve for this scalar magnetic potential. It's Laplace's equation. And if I'm hoping you might have seen Laplace's equation in some physics class somewhere, we can sort of skip right to the solutions of Laplace's equation. I'm not going to go through the whole process of the separable functions and all that. But if you've seen it, then I'm sure you've seen the spherical harmonic functions, these YLM functions in spherical coordinates. They're functions of theta and phi. And we can construct these solutions from sort of an infinite sum of these different solutions. The radial part in spherical coordinates has two specific sort of polynomials, one where it's increasing with radius, one where it's decreasing with radius. And if you figure this out, you can just take the gradient of it to get the vector magnetic field. Now, what we normally do is take that lower boundary condition on the sun, and that sort of gives us what these A and B coefficients have to be in order to match the magnetic field at the surface. And then this solution tells us how it varies as you go above the surface. Of course, if we want to just look at a simple potential field, this A coefficient is normally set to zero because we don't want solutions that are getting stronger and stronger as you go up to a large distance away. We don't want the solutions to blow up. So it's normally just these decreasing solutions, but you can match pretty much any observed photospheric field with the right set of B coefficients. If you go out to large enough number of terms in these series, and I'm sure you've seen these before. For different values of L, these different things have names. Monopole, dipole, quadrupole, octopole, and you've seen what they look like. We know there are no strict magnetic monopoles, so normally the L equals zero terms are set to zero. If it did exist, it would be a magnetic field that drops off, and the field lines all sort of point radially away from the monopole source and drops off as 1 over r squared, much like the electric field from a point charge. But for a real magnetic field, it's dominated by these higher ones that drop off more rapidly and represent more complicated sets of plus and minus magnetic polarity, pointing in or out of the spherical surface. All right. So hopefully that's a straightforward thing. That's the classical potential field solution. But there's a problem with it for the sun, and that is that all those magnetic field lines are closed. We know, as I said before, all magnetic field lines do have to be closed, and that makes sense. But we know that for the sun and the corona near the sun, the solar wind stretches them open. So there have been a series of sort of mathematical tricks that have been proposed to mimic the effects of the solar wind stretching open the field. So I want to talk a little bit about this technique called the potential field plus source surface idea that Altshuler and Schatten and others worked out. It's really just the same solution that we looked at, but with an extra little constraint on the relative values of the coefficients in front of the two terms, right? Here's that decreasing term and here's that increasing term. But if the coefficient on the increasing term is written in a specific way with a minus sign on it, then that means that the value of the potential at some radial distance above the surface of the sun that I'm calling RSS, it's called the source surface. It's normally about 2.5 solar radii above the surface. If you plug in RSS for little r, you actually get 0 here. So in other words, the coefficients of the decreasing and the increasing term have been sort of fine-tuned in order to cancel out exactly at some radial distance. And then above that radial distance, we just assume that the potential remains 0. It's very simplistic, but what it actually gives is something that looks like what the solar wind actually does to the magnetic field, right? If this potential is constant on the source surface, even if that constant is 0, then the magnetic field that's consistent with that is purely radial. It's a purely monopolar looking magnetic field, but it's not a monopole because the parts that are connected to magnetic field lines that are pointing out are pointing out. The parts that are connected to field lines that are pointing in are pointing in. It's sometimes called a split monopole. It's not exactly always split into two exact hemispheres. Sometimes the boundary between those two regions is sort of a wavy surface and not just a great circle around the sun. But there's no magnetic monopole here because just as many field lines that are leaving are coming back in. It's just shaped in a similar way as a monopole with the 1 over r squared dependence in the field lines pointing radially. But yeah, it's like I said, it's a way of mimicking what the solar wind actually does, just with this mathematical trick. And this has turned out to be a very, very useful tool in modeling the solar corona and also in space weather forecasting. And we'll see how it's still a very frequently used tool. It's computationally very fast. It's very efficient. It's easy to do, right? If you have the solar surface, the solar photosphere magnetic field, and it's broken up into those spherical harmonic components, you know the function. And if you choose a value for this source surface at about 2.5 solar radii, you get qualitative features that look very much like what the sun really does. This is just a comparison between a potential field source surface model and a 3D MHD calculation from Pete Riley with a solar minimum example and a solar maximum example. It's not perfect. It doesn't exactly look like the sun. It doesn't have these more cuspy pointed helmet streamers because of the finite nature of this source surface. But the overall openness and closedness is pretty similar. And yeah, there's all sorts of tools. You can go online and find these things. There's a PFSS Pi package that you could import into Python and compute these things for yourself with relatively little headaches, I think. I think that is about all I have to say about this. As I said before, between the PFSS and the full 3D MHD, I had sort of 4 or 5 other models in between. I'm not going to have too much time to talk about them. I just give a quick reference to one of them here that tries to split the difference. It's a little more computationally intensive than PFSS, but it's nowhere near as complex as 3D MHD from Rice and Yates. Yeah, Tom. You're muted.
Yeah, I had a interesting thing to think about for the students, and that's that the lower boundary of all of these models that you're showing here is a spherical sun, the magnetic field measured all over the sphere of the sun. And if you think about it, how would that be done? Because we only see one hemisphere of the sun at a time, right? So you have to come up with kind of clever ways to essentially measure the sun on the hemisphere that the magnetic field on the hemisphere of the sun that we don't see. So, anybody have any ideas about how that might be done? I'll give you a hint. There's no spacecraft back there. And so somebody put in the chat, Marcel put in the chat, synoptic maps. And that's right. What you're looking at right here is a synoptic map, which is a fancy term meaning the sun built up into all 360 degrees of magnetic field. What we think the magnetic field is on the entire 360 degrees of the sun wrapped around a sphere. But there's two problems there. One, we don't see the backside of the sun ever. And so the only way to make a synoptic map with stuff that you've measured onto the front is to assume that it just rotates on the back and doesn't change, which is the most simplistic way. Or you can get fancy and say, well, we know how the meridional flows and the differential rotation works. So we're going to imitate those flows on the backside and just push around the stuff we see on the front side to approximate what it might look like on the backside. And that's a synoptic map. The other big problem, though, is we never get to measure the magnetic field near the poles. So above about 75 degrees in solar latitude, we're totally blind all the time. You can't measure it from the front side at all. So there's nothing to rotate onto the backside. So everything above about 75 degrees is just an extrapolated guess from what we see in the lower latitudes. So what I'd like to say in regard to this is that whenever you see these synoptic maps, and especially when you see them wrapped around the sphere like this, that is just a best guess, a best estimate as to what the photospheric magnetic field really looks like. And so all of these coronal models are based on guesses / estimates / extrapolations of the true magnetic field of the sun.
Yeah. And in fact, when you just do that process and you wait sort of half a month for the backside to come into view and gradually assemble that full 4 pi, what you usually get when you look at that is a magnetic field with a monopole component because not everything cancels out exactly to make the monopole component go away. So when you're actually building these things to use as lower boundaries, you have to explicitly zero out any monopole components that you get from this process. Yeah. Oh, also Amanda asks about a way to see behind with I guess helioseismology. You can actually see whether there are things there, but you can't actually measure the strength of the magnetic field that way.
Yeah, that's kind of an ongoing research topic is to how to, and some people are even looking at machine learning models to basically guess what the magnetic field of those backside active regions are that you can detect with helioseismology. And that might actually be producing things that are usable in the future. So in the near future, we might be able to get the far side of the sun mapped pretty well to make a more realistic synoptic map for everything but the poles, where since we never see those, there's nothing to extrapolate. There's no helioseismological help up there. And if you notice, a lot of these models get kind of, especially during solar maximum, get kind of complex at the poles. So when you get the poles wrong, you can get the field very wrong.
Yep.
And the only way we're ever going to solve that is to get spacecraft that are orbiting out of the ecliptic and looking down on the poles of the sun and actually measure those magnetic fields. So until then, it's going to just be as accurate as we can get it, which in some cases, as Pete Riley and others have shown, is sometimes off by orders of tens of percent.
Yeah.
Grains of salt.
And well, the polar field magnitudes can be off by factors of 2, 3, or 4 sometimes also.
Yeah.
That's tough.
Yeah.
Yeah. All right. No, that's great. So yeah, so we'll be picking back up on this when we talk about space weather forecasting later. Even just forecasting the so-called ambient solar wind that we're going to be talking about. Not even going to the forecasting flares and bursty events like flares and CMEs, but just forecasting the ambient solar wind and what's going to pass in front of the Earth depends a lot on these kind of details. All righty, and I think that brought me to the end of that first part, and I wanted to talk about the solar wind now. Right, that's the thing that's stretching the field lines open. I always like to go back to history for some of these things and see how we came to know what we know. And it turns out, we're going to be talking about Parker's 1958, prediction of the solar wind. But I think it was pretty much the full century before that where the evidence sort of started and kept accumulating for something that sort of starts on the sun and keeps on going out to the vicinity of the Earth. And there were sort of three pieces of circumstantial evidence that Parker had. One of them was, of course, the existence of space weather. And even this very first event that Carrington saw the very bright solar flare and sketched it in the lower left there. And then several days later, people all around the world saw, these strong geomagnetic storms and auroras that caused things to happen. The fact that there's a cause and effect relationship, that something happened on the sun, and then several days later, something happened on the Earth, that started to become in the zeitgeist, right? It started to become in the overall mind. For an encyclopedia article that I wrote a couple of years ago, I started to try to collect some quotes in between the Carrington event and the first few decades of the 20th century when Parker and Chapman and others were starting to formulate models. And there were some interesting quotes in the middle there that talked about, these things that we measure on the Earth should be regarded as manifestations of an unknown cosmic agent of solar origin. That was Birkeland. Birkeland also modeled these things. He also produced these things in the lab. These spheres that I'm showing here was this thing he called a terrella, or a little Earth, basically a charged metal sphere that you bombard with free electrons from a cathode ray tube, and you can actually image the glowing plasma and the magnetic field lines, and you start to see things like the auroral oval, like on the Earth, or things like magnetic field, particles tracing out magnetic field lines if you put a magnetic field on the ball. So it was really kind of cool to see people trying to understand these things in many different ways. Yeah, lots of other quotes about things happening on the sun and having an influence on the Earth and expanding outwards. That's all sort of one piece of circumstantial evidence. The second one is comets. Astronomers have been looking at comets for a long time. And, at some point, they realized there were sort of many comets have two distinct tails, a dust tail and an ion tail. I guess spectroscopy can help you tell the difference between those. The dust tails are very sort of ballistic. The particles are just sort of ejected and they trail behind along orbits, around the sun. But the ion tails are always pointed virtually directly away from the sun. So the idea there is that something from the sun is blowing the ions off of the comets. Biermann sort of collected a lot of this information in 1951, published this paper in German, really nice long German name there, of the fact that many of the things that are kicked off of these ion tails flow out at speeds of something like a few hundred kilometers per second. And he talked a lot about the idea of solar corpuscular radiation, which was just really another name for particles flying out from the sun. I guess the word plasma hadn't yet become universally applied to gases of charged particles. So other terms like this were sort of used. But yeah, the sun is producing things that are flying out at hundreds of kilometers per second. And also, of course, if you go back to the space weather, storms and then, resulting things happening on the Earth, a few times 100 kilometers per second gives you that few days of travel time from the sun to the Earth also. So these numbers were all sort of starting to converge to a similar range of numbers. The third piece of evidence was this thing that was in the Staniwaki paper that we looked at, right? This idea that if we do have a hot corona and we assume it's sort of that there's spherical symmetry, it really can't exist in a state of hydrostatic equilibrium with a zero flow speed. Because if you do that and you figure out what the gas pressure has to be at large distances from the sun, say using Chapman's model of heat conduction that we sort of talked through a little bit before, the pressure reaches this constant value. And when you work out the value of the constant value, it's something. But then when you ask the astronomers, what is the typical pressure in the interstellar medium, in our local, corner of the galaxy, you get numbers that are, 9 to 10 orders of magnitude less than that. So there's this huge pressure difference between this hydrostatic corona and what we know to be out there between the stars. And if you were to set this up as a simulation, right? If you set this up, say, as a large balloon filled with this very high pressure gas near the sun, surrounded by very low pressure gas, and you let it go, what would happen? Of course, it would expand, right? It would expand out very, very far, maybe parsecs of distance, before it eventually comes in, before the pressure decreases to the point where it comes into equilibrium with the interstellar medium. But by that time, the pressure left over inside the balloon is going to be something close to this much lower level. But we know from observations that these values in the corona of similar values to this 10 to the minus 5 are actually what we see in the corona. And it just doesn't work. Something about this entire model just doesn't make sense. And this is what Parker realized also. And he sort of combined it with these other ideas of things flowing from the sun to the earth. And yeah, so there was the paper. I'm listing it as 1958A because if you actually go into ADS and look for his papers from 1958, I think he has something like 9 or 10 of them. It was one of his miracle years. Einstein's miracle 1905 year. I think this was Parker's year. But yeah, he basically put all these pieces together. The gas from the sun, from the corona, has to be in this continual state of expansion. I just put some other miscellaneous stuff about him. He's the first living scientist that NASA decided to name a space mission after, and I've got a link here to an interview with him from a few years ago that was very, very nice. It's a short 2 or 3 minute video, but it's really nice. He published this paper. Somebody in the Slack said that it was rejected. I don't know if that was quite the case. I think at this time, many papers were not sent out to external referees. They did sort of internal refereeing amongst the editors of the APJ. This was Chandrasekhar's time as the chief editor. And I'm not sure if it actually made it out to an external referee to be officially rejected, but there was a lot of back and forth of skepticism about it. But the nice thing, I had
heard that it was thoroughly rejected by 2 actually referees.
Oh, okay.
And that Chandrasekhar had to make a decision to publish it above the rejections, and he did so. Okay. Of course, they were both at Chicago, so they were colleagues, and the story goes that Chandrasekhar just said, I've read it. I think it should be published, and he published it regardless of the very vehement rejections from the referees, and the rest is history.
Yeah. And the nice thing about that history was that he didn't have that long to wait for sort of complete vindication, because people were starting to launch spacecraft out into into space. And, it was only a few years before deep space probes were leaving the Earth's magnetosphere. Some of these early, Russian and American probes didn't quite have the full complement of instrumentation on them that would have allowed the exact measurements of temperature, density, velocity, all the things that we really want to measure. It wasn't until 1962 that Mariner 2 was on its way to Venus, and Marcia Neugebauer and others had the right set of instruments on there, and they really confirmed the predictions from Parker. So yeah, it was the discovery of the solar wind only about 4 years after the prediction. All righty. And of course, since then, we've explored the solar wind in numerous other ways. We've gone closer to the sun, with Helios in the 1970s, and Parker Solar Probe, of course. We've gone much further from the sun to sort of pass into the interstellar medium. Most of those spacecraft have remained close to the plane of the ecliptic, but on the right there was also the Ulysses space probe that went out to Jupiter, got a gravitational assist that sort of kicked it 90 degrees and put it into an orbit sort of orthogonal to the plane of the ecliptic, so it could explore the high latitudes above and below the sun. Unfortunately, Ulysses originally had telescopes on it, on the mission, but they were descoped. So the actual Ulysses mission did not have any remote sensing imaging or telescopes on it. So it was really just a pure in situ mission. So it could not look down on the north and south poles of the sun, unfortunately, but it sampled the plasma up there. And just a quick sample of what we see. I think on the first day of class, I showed this sample of solar wind speeds over the course of a year near the orbit of the Earth. You can go to NASA's Omni site to get pretty much continuous data at that vantage point from the 1960s to the present. There's the fast solar wind, the slow solar wind. It's not truly a bimodal distribution when you actually measure this out. There's sort of a central peak at 450 to 500 or something. But yeah, you can see the variations. Then there's what Ulysses actually saw during its polar passes. So what I'm plotting here are solar wind speeds, but they're plotted in a polar plot, sometimes called a dial plot, where the distance from the center is the speed, but the angle and the latitude is the actual angle and latitude. The y-axis, the upper y-axis is the North Pole, then it's the South Pole, and the ecliptic plane is the horizontal axis. So we're seeing what Ulysses saw as it swept around. And at solar minimum, it tended to see very fast solar wind above the poles. The solar wind connected to those coronal holes at the North and South Poles is colored in blue. Everything else connected to streamers and active regions is colored in red and orange. And that's sort of a more chaotic, transitions between fast and slow solar wind, sort of like what we see in the upper plot there. And yeah, at solar maximum, it's just a mess of, fast and slow at all latitudes. But yeah, just wanted to give you a summary of the types of distributions of speeds that we see. But then I do want to go through the physics of this hydrodynamic solution that Parker worked out. Again, it was in, many of these details were in Iwaki's paper, but I just want to go through some of them just so we can understand what's going on. So we're going to assume that everything is time steady. Now, of course, there's in the regular usage of words, the word steady and the word static are sometimes interchangeable, but here we mean different things, right? Time steady means that the time derivatives are equal to 0. Static would mean that there are no flows, but here we're allowing for flow. We're assuming everything's spherically symmetric, sort of consistent with the PFSS, radially flowing field, radially pointed field lines, but we don't really need to think of MHD forces if we're going parallel to those field lines. And Parker started off by assuming that the temperature was constant everywhere, right? That Chapman model had the temperature dropping off as R to the minus 2/7. So this is the assumption that 2/7 approximately equals 0. So it's just a very slow, essentially negligible drop off with radius. So yeah, we can look at the mass conservation equation of hydrodynamics, the momentum conservation equation. If everything is time steady, mass conservation is pretty simple because R squared times density times flow speed is just a constant. And if you multiply that by 4 pi, you get the so-called mass loss rate of the solar wind, essentially the total amount of mass that's ejected per second over the full 4 pi of this spherically symmetric thing. You saw in Iwaki's paper that Parker's original model does not predict the value for this mass loss rate. For that, you really need to know how much gas is sort of injected at the base of the corona. It's sort of consistent with this base solving for the idea of solving for the base pressure from these models like RTV or Martin's that we looked at before. It's sort of a separate problem that you need to figure out. And then you can see how the solar wind drags that material out using Parker's model. And there's things you can do, right? You can take this pressure derivative. If the temperature is constant, you can write it in terms of a density derivative and have this isothermal sound speed pulled out. You can take the density derivative and write it in terms of the velocity derivative using the mass flux conservation equation. And you can plug this back in. And I guess I'll just show you what it looks like at the bottom left here. You get some terms multiplied by the radial spatial gradient of the radial flow speed, and then terms on the right-hand side. Right? There's a positive term that ultimately comes from the pressure gradient. That's the outward force that pushes you out. And then there's a negative term for gravity that pulls you back in. The left-hand side can be positive or negative, depending on whether it's subsonic or supersonic. There's some counterintuitive things about compressible flows where you can go faster or slower than the sound speed. Sometimes you can have a force pushing on something, but you'll slow down depending on whether you're subsonic or supersonic. It's kind of counterintuitive. But Parker was a very mathematical person, so he basically looked at this equation as a differential equation. Here's the slope u as a function of r in terms of r and u. And the nice thing is, if you can get a differential equation into a form like this, you can learn a lot about the solutions without integrating anything, right? Because what you have here, if you just look at the two-dimensional space of speed versus distance, at every point in this space, you can solve this right-hand side and get the slope. And that's sort of what I sketched out here, right? There are points, where the numerator is positive, the denominator is positive, so the slope is positive, and then negative, positive, positive, negative, negative, negative. And you can see what the solutions generally would look like. But there are some places where it gets tricky. There are singular points, right, where a equals b, and if they're both functions of r, that happens at a certain radial distance. Then the numerator is 0, so the slope is flat. That's these little horizontal lines here. When the denominator is 0, but the numerator is not 0, you have an infinite slope out of these. That's these vertical lines here, not quite physical. When both the numerator and the denominator are 0, that happens at one unique place where these two gray lines cross. 0 over 0. So guess what? You have to pull out L'Hopital's rule to get the actual value of the slope at that point. It turns out there are two solutions. And one of them has a positive slope, one of them has a negative slope. So right at the center here, you can imagine drawing an X. This is called an X-type critical point because you have two different slopes that can go through it. And we can look at the values of these A's and B's to figure out where actual values of this radial distance, where the critical radius is and the critical velocity. The critical velocity is pretty straightforward because the critical velocity is just the sound speed. So everything below is subsonic, everything above is supersonic. The critical radius looks like this, and it's kind of interesting that when the gas pressure force is higher, that means that the corona is hotter and there's a larger sound speed. That means that this R sub c is smaller, so it's closer to the sun. And the physics of that means that the gas pressure gradient force beats gravity sooner, right? This critical radius is the place where the gas pressure gradient force balances gravity, and it wins above that and gravity wins below that. So if that's pushed closer to the sun, that means you have a stronger force, a stronger gas pressure force pushing things out, and you get that from a hotter corona. All right, so this upper left plot sort of shows you what you sort of do to sketch out the slopes. But if you really do it numerically, you get something like this lower left plot. And there was some confusion about a version of this in the Waukee paper, but I think something like this might be a better way of stepping through it, because you're essentially connecting these little line segments with smooth curves. And yeah, so we want to figure out, what does the sun actually do here? Because there are all sorts of possible solutions, and we want to know which ones correspond to what the sun actually does. We can rule out a bunch of these things, right? The ones that pass through the infinite slope, right? The green ones on the left and the orange ones on the right, we can sort of consider those as not being physically real, because there's two solutions for the flow speed at a given radius. They're double valued. The real world doesn't usually like to do that. It wants a unique solution at a certain distance. There are the cyan curves at the top and this black dotted one that goes down through the critical point. Those I think we can rule out, because as you go really close to the sun, the speeds get very, very high. And near the sun, we don't tend to see huge, fast outflows of the solar wind. The observations tend to show that the solar wind is very low velocity near the sun, and it accelerates as you go out. So that points the way to these last two solutions, right? There's the solid black solution that's increasing through the critical point, and the dark blue ones that always remain subsonic. These are the so-called solar breeze type solutions. And they were popular for a while in the late 50s and early 60s. But in general, once people found out that when you go all the way out to infinity, the wind speed goes down to zero, and you have the same problem that you had with the hydrostatic solutions. You have a very large pressure. It just doesn't match the interstellar pressure. So Parker said, well, by the process of elimination, the only thing left is this thick black solid line that increases. It's subsonic below the critical point, supersonic above the critical point. And he suspected that was the true solution. And I think some of those negative referee reports were basically saying, why would the sun pick this one sort of fine-tuned just so solution that passes through this critical point, especially because if you're approaching it and you're just a little off, you might veer off onto one of these green ones or veer off onto one of the blue ones. Why would it know to go through that exact point? It turns out that when you start to look at the time variability of this system, which we suppressed, right? We got rid of all the time derivatives. But if you put that back in and look at the stability, it turns out that this increasing transonic solar wind solution is a sort of a stable attractor of the system. If you start off on one of these other solutions, it will evolve onto that transonic solution. Marco Velli proved that very nicely. It took many decades to do that, from the 1950s, but in the 90s, it was actually, I think, nicely proven. So yeah, the differential equation can actually be integrated. It's separable. There's functions of u on one side, functions of r on the other side. So you can integrate. The problem with this is you can't quite solve it for u as a function of r. Turns out you can actually, if you use this Lambert W function that you might have seen in math physics classes. That's kind of a nice way of solving the equation. But in general, people do this numerically. I think Parker sketched out these solutions by hand, but after solving them, either I forget whether he solved them with a computer or not. But yeah, that's definitely hand-drawn figures in the APJ from the 1950s. And yes, you see that higher temperatures lead to faster outflow speeds, like you'd expect. Yeah, there's other ways of looking at this. In the paper that we read for this week, you can also solve Bernoulli's equation, essentially using the energy balance arguments to try to understand the solar wind. And this allows you to get away a bit from the isothermal assumption, the constant temperature assumption. You can assume different adiabatic variations of temperature and density and pressure as a function of distance. And yeah, we're getting to the end here, so I don't know how much it matters here. Question in the chat about, is it a coincidence that the critical point is right around where the source surface is at 2.5 solar radii? You know what? I don't think it is a coincidence, but it's surprisingly difficult to actually work out the full chain of events that would cause the solar wind to be pulling out the magnetic field into this radial direction right at that point. There are other studies of the solar wind that say that there's a lot of other interesting things happening out at 10 to 15 to 20 solar radii, the so-called Alfvén point, where the solar wind speed exceeds the Alfvén speed. And that's the place where it really seems to be that you lose the ability to have closed field lines and everything has to be all open. Why the actual appearance of the solar wind stretches things out much closer to the sun than that 10 to 20 I think everybody knows how it works in the numerical simulations, but how it actually, I don't know if there's a nice physically intuitive way of talking about that. But yeah.
Steve, isn't the source surface location kind of a parameter you can set in various models? And so 2.5 may be kind of a traditional thing that people just set, thinking it matches the critical point. Let's put it there and see what it looks like. And it looked okay.
I don't know.
I've seen models where they've gone to 3 or 2 and they just mess with it until it looks right.
Yeah, but the fact that it tends to look right not too far from 2.5 in either direction.
Yes, it must be telling us something, but
Yeah. But there are many other solar wind models where the distance of the critical point can be anywhere from, you know, 0.5 solar radii above the surface to 5 or 6, right? There's a whole lot of variation there.
yeah.
Yeah. Oh yeah, another, like I said, if you had the temperature as a function of distance, you know, as sort of a table, right? Essentially replace the constant temperature with some known function of temperature. You can just integrate everything numerically. These are figures from that same encyclopedia article I mentioned before. And one interesting thing about it is if you try to do your best on the left there and say, this is what I think all the different measures of coronal temperature are telling us. There's sort of a range, but there's sort of an overall radial decrease from the sun all the way out to 1 AU. If this keeps going out to 1 AU, you'd get something like we measure around 10 to the 5 Kelvin out there. But if you vary the normalization up and down, you would need to vary it by almost an order of magnitude, basically from the green all the way up to the red, in order to get Parker solar wind models with the observed range of speeds from 250 to 800 or 900 kilometers per second. But the problem is the actual measured values of temperature in the corona don't vary over that huge one order of magnitude. They really only vary over this sort of middle yellow region. And if you just put that in, you just get these middle, intermediate solar wind speeds. So in order
do those observed speeds take out CMEs?
Oh no, yeah, this is all just pure ambient, pure quiescent solar wind.
Huh. Okay.
Yeah, so there are still research questions that need to be answered here about how do you get the slowest speeds of the solar wind? How do you get the highest speeds? I think we're starting to get a feel for those answers. The slowest speeds, I think, happen due to what they call co-rotating interaction regions. Essentially, the solar rotation crashing together slow and fast streams. And when they crash together, there's sort of an increase in entropy, which slows things down. And I think these slowest speeds come about as a result of those interactions. The highest speeds, I think, come about because of other sources of momentum that are added to the right-hand side, other forces acting on the plasma, such as waves and turbulence that can accelerate the flow by several hundred kilometers per second. But yeah, there's still a lot of interesting research on those. Yeah, and that is essentially where I ended up here with introducing the solar wind. For next week, I'm proposing that we read parts of two papers that sort of I think are a bit complementary. The first one is Wang and Shealy's paper from 1990 that introduced something that we now call the WSA, Wang, Shealy, and Argy technique for estimating the wind speed just on the basis of the shapes of the magnetic field lines that you get from things like the potential field source surface method. Yeah, it's a short paper, and I think there's a skippable section in there too, so it's not too long. And apologies about plugging my own paper, but I kept looking for the paper that contained the right kind of follow-up on Wang and Shealy that talked about the physics of why is the fast wind fast, why is the slow wind slow, and I couldn't find anything other than this paper I wrote in 2005. And it's just a few sections of it that I suggest. But again, apologies for the indulgence there. But I think between the two of them, I think it'll give a nice setup for our later discussions of forecasting the wind speed on the basis of things like the potential field. So yeah, I'll start a paper 4 discussion channel, and I guess that is all I have for right now. Any questions based on that? Feel free to continue the discussion in the Slack too. I don't cut it off on the day of the class. We can keep chatting about things there too.
Thank you so much.
All righty, stop the recording.
Thank you.